Yeah, thank you for the introduction. Yes, so in this talk, I'll give a general overview of MaterialX, mostly aimed at people that are not familiar with the project, so sorry for everyone else. I'll start with a brief recap of the project's history and the important milestone that it has hit so far, and this is followed with an overview of the current state of MaterialX, and I'll finish with some exciting new developments. Okay, now let's start with the most fundamental question. What is MaterialX? I think this sentence from the MaterialX specification captures the essence of the project quite well. In short, MaterialX is a standard to describe the look of CG objects with the aim to simplify the sharing of assets across a wide range of content creation and rendering software. Now, the project was launched at Industrial Light and Magic in 2012. At the time, OpenEXR was an established standard for image storage, and Alembic was gaining traction as a standard for geometry and animation exchange. However, back then, there was no industry standard to describe the look of a CG object that would satisfy the needs of the of high-end movie and TV production. And this was highly problematic because the VFX work on a project is usually split among multiple vendors, and it's quite common that an asset has to be exchanged between different vendors. It also became increasingly important that assets can be used across different media types, as a number of new Star Wars projects were on the horizon at Lucasfilm at the time, and this meant that it was not just enough to be able to exchange assets across different VFX pipelines, but it was also necessary to do this across the offline rendering and real-time rendering pipelines. And all these factors then led to the development of MaterialX as a standard for CG object looks across a wide range of applications and media types. And this effort bore fruit as MaterialX was first used in production on Star Wars The Force Awakens, which allowed the assets look to be transferred for real-time for the creation of the interactive experience trials on Tatooine. Now, around the same time, Autodesk was also looking into solving the problem of portable materials. And after some discussions between Autodesk and ILM, it became clear that joining forces would benefit both efforts significantly, leading to the first partnership in this project. But it was also obvious that an effort like MaterialX would only be successful through wider industry collaboration. So in the same year, the first version of MaterialX MaterialX specification was publicly released. And it's also interesting to note that ILM initially focused on pattern graphs that are used to define the texture of an object. Early version of MaterialX were mostly agnostic to the part of the shader that is responsible for the light transport. And Autodesk, on the other hand, they have experimented with a system that generates shader code based on hierarchies of BSDF building blocks, and these developments later resulted in the physically based shading nodes and the shader generator that exists in MaterialX today. But I will talk about this more later. Releasing the specification was just the first step. In order to accelerate the adoption of MaterialX, the project went open source in 2017, and the repository is hosted on GitHub and contains the MaterialX specification and a suite of tools and libraries that complement the standard and facilitates the integration of MaterialX into existing applications. From this point on, the project has experienced steady growth, and the pace has picked up quite significantly as more, in recent years, as more organizations have joined the effort. And this has led to a continuous expansion of the specification and feature set, through contributions from the community. Here's just a small selection of some of the most important collaborators. The project has not only grown through contributions to its code base and updates to the specification, but it also through industry adoption. Arnold was the first commercial software to support MaterialX, facilitated through an early partnership between ILM and Autodesk, and it also has played an important role for USD since its early days. And fast forward to today, and we see that MaterialX has been integrated into some of the most important graphics software packages. It ranges from open source real-time web frameworks to commercial software for high-end movie and TV production. And another important milestone for the project was its adoption by the Academy Software Foundation in 2021, and after an initial incubation period, the project has fulfilled all the requirements to be certified as a hosted project. There has been a strong collaboration between USD and MaterialX for some years, and this has ultimately led for MaterialX to become the default in USD in 2023. Yes, but that's now enough about the past, and now I want to switch to the current state of MaterialX. MaterialX represents materials as shading graphs made up of shading nodes. The MaterialX specification defines a set of standard shading nodes of various types, but MaterialX is more than just a specification. It also comes with a set of useful tools, such as an editor, viewers, and a shader generator. And it also has definitions for common surface shading models, as well as a shader translation system. I'm now going into each of those features individually, and will also highlight some of the newer additions. Yes, so MaterialX defines different types of nodes, and one of those types are pattern nodes. These nodes usually operate on scalars, colors, or vectors, and they are used to model the texture of objects. Pattern nodes have been part of MaterialX since the very beginning, and new nodes are added on a regular basis. Now, the current set of nodes consists of nodes for reading texture, applying triplanar mapping, for reading geometry properties like normals, tangents, and user-defined properties. And there's also a set of nodes for procedurals to generate procedural patterns or noise functions. And the outputs of those nodes can be further processed with math nodes or combiners or color correction and similar nodes. And I also want to point out that a new version of MaterialX was released in January this year that included improvements to the Whirly noise nodes that make it possible for the cells to be filled with constant values. This is, for example, important to model metal flakes. Another addition was a new node for generic color ramps. Yes, and MaterialX also supports physically based shading nodes. These nodes represent the light transport part of a shader, and so they open up the possibility to fully express shading models with MaterialX building blocks. And here's a selection of some of the BSDF models that MaterialX supports. And in the release in January, there was also an addition of a hair shading model based on the Chang hair BSDF. But most of those individual BSDFs are not that useful on their own. This is why MaterialX also defines utility nodes to combine BSDF. Here's an example of dielectric layered on top of a diffuse BSDF using the layer node. And here's another example of a diffuse BSDF mixed with a conductor BSDF using a mix node with a 50-50 mix weight. You can see that these combiner nodes make it possible to define complex shading models just with MaterialX nodes. But MaterialX does not just define nodes that represent surface-based distribution functions, but it also defines physically based nodes for volumetric effects, and currently it supports two models. The first is just a simple absorption-only model, and the second is a model for a complete participating medium using the HG phase function, and it comes with the usual parameters for the absorption and scattering coefficients and the phase function anisotropy. It also has a number of nodes that represent emission distribution functions that can either be applied to lights or to surfaces. Here are two examples of emission from a surface, and the first is simple uniform EDF, and the second is a generalized Schlick EDF that has an angle-dependent emission based on the generalized Schlick-Fresnel approximation. I'm just showing this for completeness, but of course MaterialX also has a displacement node that can be used to apply modifications to geometry. And finally, I also want to point out that MaterialX has a small library of nodes for non-photorealistic rendering, and this is becoming more and more important as more animated movies are turning towards stylized looks. This NPR library includes nodes to retrieve the view direction, compute the phasing ratio, and has a Gooch shading node, among others. Okay, now let's zoom out and have a look at what you have seen so far. So we have seen that MaterialX defines a set of standard nodes for patterns, as well as physically based and non-photorealistic shading nodes. However, this is obviously not enough to define a standard for portable materials. That's why it also defines a schema to describe the interface and additional attributes of nodes and their inputs and outputs. And these attributes are, for example, used for color space management or for handling units and to specify UI-related properties. And the schema also defines how nodes are instantiated and assembled into graphs. And it has a type system with built-in types and a mechanism to define custom types. And all this data is stored using an XML-based file format, and the image on the right is an example of this. So this is a node implemented with or defined with a custom node graph. And as a side note, MaterialX also defines an optional extension to assign materials to, or materials and properties to geometry. But this is usually handled by USD or any application-specific mechanism. And to simplify working with those MaterialX files, a graph editor was contributed to the MaterialX project in 2023. It lets you load, edit, and save MaterialX files, and it also has a property editor and a real-time viewer of the material. And it's also worth mentioning that there's an alternative open source MaterialX editor called Quiltix. However, this editor is not part of the MaterialX project and is hosted in a separate repository. And apart from the open source editors, there are also some of the commercial packages support MaterialX graph editing, such as Houdini and LookDefX in Maya. The MaterialX project has additionally two real-time material viewers. On the left is a desktop-based viewer written in C++ using OpenGL and Metal, and on the right is a JavaScript-based web viewer based on the Free.js framework, and it uses the MaterialX JavaScript bindings. And both viewers let you load MaterialX graph and edit their properties interactively. Now, one way to integrate MaterialX into a renderer is to implement the standard shading node natively, and this is what has been done in some cases. But another option is to make use of ShaderGen. ShaderGen is a library that's part of the MaterialX project that lets you generate shader code based on MaterialX graph, and various backends have been implemented over the years. So currently it supports GLSL, OSL, MDL, and MSL. And the idea is that an application would pass the MaterialX graph to ShaderGen, which would then generate the shader code that can then be consumed by the application for rendering. And this is also what the MaterialX viewers and the editor do. And it's also worth mentioning that the latest MaterialX release in March brought some performance improvements to this shader generator. Now, in order to generate any shader code, we first need to be able to, some shading networks. And over the years, various organizations have come up with physically based shading models with various functionality and capabilities. And thanks to the modular nature of MaterialX, it is possible to express these shading models as MaterialX graphs. And the consequence of this is that if a renderer implements all the MaterialX standard nodes, then it is capable of supporting these shading models. And this is an ideal situation from a more material portability point of view. And there are currently definitions for Autodesk Standard Surface, OpenPBR, USD Preview Surface, GLTF, PBR, Llama, and just recently Disney Principle was added, and you can see the shading network on the right. And one model I want to point out in particular is OpenPBR. It is a new open shading model that was developed in collaboration with Autodesk and Adobe, and was publicly released last year. And this project is organized as a sub-project of MaterialX. And in fact, the reference implementation is actually a MaterialX graph. Now, in an ideal world, all rendering systems would fully support all the MaterialX shading models. However, this is not really a realistic goal in practice for various reasons. Another difficulty are proprietary shading models, because companies might not want to disclose all the details of their shading models. And even if they could be represented by a MaterialX graph. And for cases like this, MaterialX has a shader translation system that uses MaterialX graphs to translate from one shading model to another shading model. And the shader translation graph can either be hooked into the rendering system directly, so it would run on the fly as part of the shader evaluation, or the translation can happen ahead of time on baked textures. Now, the shader translation graphs that are currently available can translate from OpenPBR to Autodesk Standard Surface, or from Autodesk Standard Surface to OpenPBR, USD Preview Surface, or GLTF PBR. Here's an example of this shader translation graph from Autodesk Standard Surface to USD Preview Surface, shown here in Maya LookedFX. And as you can see, the shader, the target shader has less parameters than the source shader, or in other words, the target shader is not able to replicate all the effects of the source shader, and for this reason, in this case, the anisotropy is averaged, and the sheen and thin film and subsurface effects are ignored. Here is an example comparison between Autodesk Standard Surface and the translated USD Preview Surface, shown here in the MaterialX viewer. It's quite close. The only visible difference here is the highlight in the rightmost example. In case of Autodesk Standard Surface, the highlight is elongated because of the anisotropy, but because USD Preview Surface does not support anisotropy, the highlight is circular in this case. And we had a project at ILM a few years ago where we refined the shader translation to translate from one of our internal shading models to Autodesk standard surface, and this became part of a larger system to automatically export assets for external vendors. And here's a comparison between our original shading model and Autodesk standard surface with the translated parameters. Again, it's quite a close match. I think our shader, the highlight is a bit brighter. And here's another example of the BB8 asset with some additional effects like emission and transmission. Again, the results are very close. Okay, now I want to give you a sneak peek of what the future brings. A new shader gen backend has been in the works, and that lets you generate code for the web GPU shading language. And a new pattern node has been added for hex tiling, shown here in the MaterialX viewer. And both features will be included in an upcoming MaterialX release. And lastly, I want to talk about the state of MaterialX in RenderMan. So far, RenderMan has only supported the MaterialX pattern nodes through USD via its Hydra render delegate. However, it does not yet support the physically based shading nodes as specified by MaterialX. And this is why we started a collaboration with Pixar last year to finally bring the MaterialX BSDF to RenderMan XPU. And once the work is finished, RenderMan XPU will be able to support arbitrary MaterialX shading graphs. For example, OpenPBR and Autodesk Standard Surface will be supported through the MaterialX implementation. And the BSDF nodes that have currently been implemented are Ornaya Diffuse, Burley Diffuse, the Conductor, Dielectric, Generalized Slick, Sheen, and Subsurface. And the work to implement the utility nodes to combine the BSDF, so the layer and mixing, is still ongoing. And now I'm going to show you a demonstration of the existing BSDF in action. This was rendered with RenderMan XPU in Houdini Solaris. Okay, that brings us almost to the end. I just want to reiterate that the fast progress in recent years mainly comes down to the active engagement of the community, and the stats show us that there has been a constant stream of contributors over the last year, and now we are at over 250 contributors in total. And these contributors are associated with various organizations that are that are helping pushing this project forward. And finally, I want to thank everyone that contributed to this presentation in one way or another. And for more information about the project, visit materialx.org, or if you have any questions or topics to discuss, then drop a message on the MaterialX Slack channel. I also want to point out that the ASWF organizes regular Dev Days events where interested people can participate in a hackathon to contribute to one of their projects. And the last Dev Days event has resulted in 10 merge pull requests for the MaterialX project, so it was quite successful. And the next event is on the 25th of September this year. So that's all from my side. Thank you very much.
All right, thank you so much. Do we have any questions from the audience? All
right. Great talk. Can you comment a little bit on the, let's say, whether the gaming industry has seen MaterialX as a useful tool. What's limiting the adoption?
Yes, yeah. Maybe you've seen on this slide that there has been, it was integrated into Unreal Engine. So like there is currently a way to import MaterialX assets into Unreal Engine. Now internally it will still be converted into a representation, like a proprietary representation from Unreal Engine, but it helps, like if you have create an asset in a DCC and export it via UST using MaterialX, then you can import it into Unreal Engine. Yes. I don't think there has been any adoption by Unity so far. Yeah.
Okay, any other questions? Yep.
Thanks for the talk. There is more and more geometry in materials. So you mentioned displacement, but how about vector displacement of fuzz, fibers, like more geometric content in the material? How is MaterialX dealing with that?
Yeah, MaterialX itself doesn't like handle the geometry aspects that you would need in another format, right? Or are we talking about shaders to modify the geometry and these kind of things?
No, really the geometric component of materials.
Yeah, that's currently not not covered. Yeah.
Yep, got another question over here.
Thanks for the talk. It's really cool seeing how this has evolved over the years. I was wondering, kind of in line with the earlier question, do you know if there are efforts towards kind of making it more suitable for real-time use?
Making MaterialX more suitable for real-time use?
Right, just higher performance kind of meant for real-time rendering. It seems like it's mostly designed for offline things at the moment.
MaterialX was designed with like all kinds of renderers in mind. So it doesn't impose like strong restrictions on like certain shading models. I mean, the MaterialX viewers, they all run in real time. And it's also okay if a render needs to make compromises on shading models just to run in real time. That's perfectly fine. I mean, the goal is not to have total parity across renders. I think that's not possible, at least not right now. So graceful degradation is, I think, the way to go, right? Yeah. So I don't think MaterialX is really like imposing any restriction that would prevent it from being used in real time.
Hi, thanks. A pretty good talk. It's nice that you're now able to represent all these standard materials via a shading graph. Do you have any information about the overhead that introduced? Like if somebody would just take OpenPBR, write down handwritten, hand-optimized code for the shader compared to the shader network evaluation, and then the generated code with that. Like, do you know if there's any big overhead or downside on that?
Yeah, I mean, there are a lot of different steps involved in this, right? It also depends on how you integrate MaterialX. Like, are you running the shader generation as part of the rendering process, or are you doing it ahead of time? Yeah, and I mean, the different individual parts of the shading nodes are kind of hand implemented, and then the shader generation aggregates those into like a full shader based on the shading graph. And yes, and then it just produces shader code, and this still goes into some compiler, right? Like in an OSL, it would still go through like the compiler that does like very aggressive constant folding and these kind of optimizations. Yes, so there is an overhead in terms of, yeah, compiling the graph down into shader and then compiling this again into machine code. But then during rendering, I think if the building blocks have been implemented in a proper way, then it shouldn't be too much overhead. but obviously, you can always do, like, you can't be like generating a whole, programming a whole shader, just the whole thing, and being able to do optimizations is obviously much faster than if you have a shading graph with individual base building blocks where you can't really do smart tricks. You just have to rely on the compiler and the tools to do the optimization for you, but yeah, obviously they can't do like any smart things that a human could do, yes.
Great. Well, I think we're out of time. Let's thank Alain.